In this lecture, we are going to do a little warm-up as part of your journey into reinforcement learning. Like all exercising, it's important to warm up first so that you don't hurt yourself. And believe me, there will be tons of heavy lifting in this course. You can also think of this as a readiness test of sorts. You can imagine that if you struggle to lift the 50-pound warm-up weight, then when it comes to the 100-pound weight, you might have some issues. So this is all for your health and well-being. Let's get started. So the language of this class is going to be probability. Everything we do is based on undergraduate level probability. We're going to start with a simple question. We have two probability distributions here, P of A comma B and P of A vertical bar B. The question is, what do we call these two kinds of distributions? In other words, what do this comma and this vertical bar mean? By the way, I'm not going to pause very often in this video, so if you want to take some time and remind yourself of the answer, please pause the video on your own as we go along. So the answer is P comma AB really means P of A and B. This is the joint distribution between the random variables A and B. The other distribution is a conditional distribution. We read it as P of A given B. It's the probability distribution of A given that we already know B. Alright, next question. Let's suppose I'm given some probability distribution, P of xy. By the way, now you know that this is a joint distribution between the random variables x and y. Let's say I want to know the distribution P of y. I have two questions for you here. Number one, what do we call the process of finding P of y using P of x and y? And what do we call P of y in this context? And number two, how do we actually find P of y using P of x and y? Again, take a moment on your own and pause the video if you have to. Here's the answer. This is a process called marginalization, and in this context, we would refer to P of y as the marginal distribution. If x is a discrete random variable, we would find it by taking P of x and y and summing over all possible values of x. If x is a continuous random variable, we would find it by taking P of x and y and integrating over all possible values of x. Next question, which is somewhat related to the previous one. I have here this weird E symbol, and inside of it, I have the random variable x. As a side note, I want to mention that you may see this in slightly different forms depending on where you look. I will just use a regular E, since it's pretty unambiguous and they don't have any fancy E's in the program that I use to make these lectures. But you can also have a bolded E or a fancy E. All are valid. In addition, you might see this with round brackets, square brackets, or squiggly brackets. All are fine. Finally, yet another nuance you may encounter is that sometimes the E will be subscripted by a letter corresponding to a random variable, or it may be subscripted by whatever symbol you are using to represent the distribution of that random variable. And sometimes there will be no subscript at all. Usually that's because it's pretty obvious what distribution we're referring to. Again, all are valid. So my question for you is, given some probability distribution P of x, how can I calculate E of x? And what do I call this value? So the answer is, this is called the expected value. We can calculate the expected value in a very similar way to marginalization. So if x is discrete, we take the sum of x times P of x over all possible values of x. If x is continuous, we take the integral of x times P of x over all possible values of x. The next question is another question about expected values. Here's a similar notation, but now we have this vertical bar again, with a y on the right side of the bar. The question is again, what does this mean and how do I calculate it? So this is called the conditional expectation. It's analogous to the previous expectation we looked at. The random variable is still x, but now we take the integral over x times p of x given y. In other words, we use the conditional distribution instead of the marginal distribution. Next question. Suppose I'm given some function g, and I want to know what is the expected value of g of x. Again, we differentiate between the discrete and continuous cases. If x is discrete, this is the sum of g of x times p of x over all possible values of x. If x is continuous, this is the integral of g of x times p of x over all possible values of x. This is sort of a generalization of the expected value of x, since in the plain expected value, the function is just identity. Next question. Suppose I have some constant c and some random variables x and y. I want to calculate the expected value of c times x plus y under some distribution. It doesn't matter what distribution it is, but if you want one, then let's say it's the joint distribution between x and y. The question is, using the fact that the expected value is a linear operator, how can I expand this expression? In fact, you did not even need to know that the expected value is a linear operator in order to answer this question. This can be derived from the answers to the earlier questions. Since the expectation is a linear operator, the expected value of a sum of random variables is equal to the sum of the individual expected values, and we can bring the constant c outside the expectation. The next question is this. The expectation of x actually has a common name. What do we call it? The answer is the mean. The expected value of x refers to the true mean of x. The next question is this. We know that integrals and summations over random variables can sometimes be intractable. This is different from taking derivatives, which is completely mechanical and therefore easy. In fact, we now have programming libraries that can do it automatically. Integration, on the other hand, is almost always impossible, and is usually only tractable as an exception. So, given this fact, we typically want to estimate the expected value, instead of doing some integral in order to calculate it. The question is, if I can draw samples from the distribution p of x, how can I estimate the expectation of x? The answer is, if I can draw samples from the distribution of x, then I can just take the arithmetic average of those samples to get an estimate for the expected value of x. As per the previous questions, the expected value of x is called the mean, and thus this estimate is called the sample mean. We call this approach to estimating certain values the Monte Carlo method. For the next question, we're going to go back to probability distributions. Let's suppose I know the conditional distribution, p of x given y, and I know the marginal distribution, p of y. How can I use these to calculate p of y given x? The answer is by using Bayes' rule. In general, p of y given x is equal to p of x and y divided by p of x. That is the joint distribution divided by the marginal distribution of x. Of course, we were given neither of these, so we have to put them into terms of distributions we were given. P of x and y is just p of x given y times p of y. And as you know, p of x is the marginal distribution, which means it's the sum or integral of the joint distribution over xy, which is just the same as p of x given y times p of y that we have on top. Now again, it's important to remember that in practice, integrals and summations of this type are generally hard or impossible. We will see later in this course how they can be dealt with elegantly without having to resort to Monte Carlo methods. For the final exercises in this warm-up, we're going to switch gears a bit and talk about function approximation, better known as machine learning. We're not going to look at any fancy machine learning models in this course, just linear regression, which is usually day one in most machine learning classes these days. So suppose I'm given a set of data points, x1, y1, x2, y2, all the way up to xn, yn. In this case, we can say that the x's are d-dimensional vectors and the y's are scalars. As you know, the basic linear regression model is y hat equals w transpose x, where y hat is the model's prediction for y given x, and w is a d-dimensional vector of model parameters. The question is, in a linear regression, what loss function should I use to adjust w so that the y hats are close to the y's in the dataset? The answer is the mean squared error. It's the squared error between y and y hat for each data point I, summed for all i's from 1 up to n. Alternatively, you could also say the sum of squared errors, which is also fine. You'll just have to adjust the rest of your answers accordingly. The next question is this. Given our loss function, the mean squared error, what are two ways I can find the optimal value of the weight vector w? Here's the answer. The first method, which is the one students usually learn about in a traditional statistics or machine learning course, is called the closed form or analytical solution. We can get this by putting all of the x vectors into a giant matrix called big X, which is of shape n by d, and putting all the y samples into a giant vector called big Y, which is of shape n by 1. Then we plug those into this formula, and you get the weight vector w. The second method, which is more applicable in modern machine learning, including reinforcement learning, is gradient descent. The idea is, in a loop, we repeatedly find the gradient of the loss with respect to the parameters w, and then take small steps in the direction of the negative gradient. The size of the step is determined by the learning rate, alpha. It's important to note that gradient descent and gradient ascent are actually one and the same. Suppose I take the negative of our loss, call it a utility, and say that we want to maximize this utility. Well, if I take the gradient of this and go in the positive direction, it's actually no different than going in the negative direction of the original gradient, since you can just bring the minus sign outside. This is usually a big point of confusion for beginners, so make sure you can see how this works. The next question is this. Because we know that gradient descent is one method for solving for the optimal value of w, let's find the gradient of the mean squared error with respect to w. Of course, this would be necessary in order to even do gradient descent. So here's the answer for the gradient. One method is to state it in terms of individual samples, xi and yi, which is fine. But in code, since we normally calculate summations using for loops, we would rather avoid for loops if possible, since they are slower than more vectorized operations. And so, if we use the matrix form of our dataset, we can express the gradient as 2 over n times big X transpose times big X times w minus big Y. The final exercise in our warm-up will be a programming exercise. First, I'm going to assume you understand the importance of synthetic data, especially as it relates to evaluating the efficacy of an algorithm. So this exercise consists of multiple parts. First, you're going to generate data that is appropriate for use with a linear regression model. Second, you're going to find the optimal value of the model parameters using the gradient descent method rather than the analytical solution. This will of course involve choosing the learning rate, as well as the number of iterations of gradient descent that you need. Finally, confirm that you found the solution by plotting the loss at each iteration during the gradient descent process. This is a good exercise for those of you who perhaps haven't done linear regression for a long time, or maybe you learned it in a different programming language. This should get you familiar with the functions and libraries we'll be using in Python that are common for data science and machine learning. Alright, so that's it for our warm-up. Hopefully you did all the exercises and answered all the questions. So if you ever learn these things in school and you ask yourself, when will I ever use this stuff? Well, the answer is now, right in this very course.